Hello, and welcome to the Chapter 7.3 lecture on Laplace transforms, operational properties, part 1. So we've now learned how to find Laplace transforms and how to find inverse transforms of a number of functions and how to manipulate others to be in terms of these known forms so that we can find inverse transforms. And one thing that we've used for this is the fact that the Laplace transform and its inverse are linear. And our first operational property, the first translation theorem as we call it, is that the Laplace transform of e to the at times little f of t is big F of s minus a. So in other words, if we multiply by e to the at, then that shifts the Laplace transform to the right by a. The proof of this is just plugging into the definition of the Laplace transform. You plug in e to the at times f of t. There it is. And you can combine, and you end up getting that it's f of s minus a. Let's see an example. Let's find the Laplace transform of t times e to the t. So this is the Laplace transform of e to the 1t times t. This e to the 1t, that's our e to the at. And then that t, that's our f of t. And f of s, that is the Laplace transform of t, the original one, which we know is 1 over s squared, looking at our list. And the translation theorem tells us that this is big F of s minus a, which in this case is s minus 1. So that means that we plug in s minus 1 or s in the Laplace transform of the original. And we have 1 over s minus 1 all squared. That's substituting that s minus 1 for what was originally s for the definition of function composition. So that's convenient. Whenever you have e to the at multiplied by something of which you know the Laplace transform, you just find the Laplace transform of that other guy. In this case, it was 1 over s squared. And then you replace s with s minus a, and you're good to go. And one of our main uses of this will be for inverse transforms. And when we look at an inverse transform like this, what we can ask ourselves is, well, first we ask, is it one of the transforms on our list? This is not. And then we ask ourselves, does this look like a translated version of one of the guys on our list? And it does. It looks kind of like 1 over s squared, except we translated it with this plus 1. So what we want to do is get it in the form of big F of s minus a and see if we can go the other way. So this is 1 over s minus negative 1 all squared, just writing that plus as a minus minus, and now it looks like f of s minus a. So to be clear, where big F of s is 1 over s squared, this is f of s minus negative 1. So this is the inverse transform of f of s minus negative 1. And we know that that is e to the at, negative 1 times t, times f of t, where little f of t is that inverse transform of f of s, which is the inverse transform of 1 over s squared, which we know is t. So that's e to the negative t times t. Let's do another example. Take a look at this. Let's find the inverse transform of this function. So when we see something like this, the first thing we should think is, can I do a partial fraction decomposition? That's what we did in chapter 7.2. So what two numbers added together are 6 and multiplied are 13? Yeah, none come to mind. And if one uses the quadratic formula, then one will see that this only factors with complex numbers. So that's no good. If that's the case, then instead what we want to do is complete the square. So this is s plus 3 squared plus 4 in the denominator. If you FOIL this out, you'll get that. If you are rusty on completing the square, there are lots of online resources for how to do that. And once we complete the square, now what we can do is look and see, does this look like a translated form of anything that we have? Well, if that s plus 3 were a single thing, like s squared plus 4, then indeed, it looks like a sine or a cosine of some kind. So let's write this as s plus 3 squared plus 2 squared. And now it's looking a lot like cosine, but translated to the left by 3. So is this equal to e to the negative 3t times cosine of 2t? No, because every s needs to be translated by that same amount. After all, it's f of s minus a. That means that we're substituting s for s minus a everywhere. So for that to be the case, we would need an s plus 3 up here. So what do? Well, we can just put it there and then subtract. Have you noticed that doing nothing in a fancy way is a common theme in inverse Laplace transforms? And now we can break this up into a sum of two different functions, one of which will be this s plus 3 over so-and-so, which will be a translated cosine, and the other of which will be this 3 over so-and-so, which will be a translated sine. Now to get that second component to look like sine, what we need to do is get a 2 up there, since remember it was all over s minus negative 3 squared plus 2 squared. And the sine has that k up there, so what we need is a 2 there. So what we do is we put a 2 there and then divide by 2 on the outside to get it so that we're doing nothing. And then we also pulled out that 3. So this guy is f of s minus negative 3, where f of s is s over s squared plus 2 squared. And this guy is f of s minus negative 3, where f of s is 2 over s squared plus 2 squared. So we recognize each of these as a translation f of s minus a of something whose inverse transform that we know. So what's the inverse transform of this big F, inverse transform of s over s squared plus 2 squared? That is cosine of 2t by our list. And similarly over here, that is sine of 2t by our list. So using our translation theorem up here, this is therefore e to the negative 3t times cosine of 2t minus 3 halves e to the negative 3t sine of 2t. Now, in electrical engineering and many other applications for that matter, and differential equations related to them, there are frequently on-off switches in some sense, which are modeled by the unit step function. The unit step function looks like this. The unit step function of t minus a is 0 if t is less than a, and 1 if t is greater than or equal to a. So it looks like this. Think of it as it is off until we get to a, and then it jumps to 1 and is on past time a. And with this, we can, quote, turn functions on after a particular time via multiplying them by the unit step function. So, for example, this is the graph of 2t minus 3 times the unit step of t minus 1. Imagine if it continued, then we would have our y-intercept of negative 3 with a slope of 2. So that's 2t minus 3. And what multiplying by the unit step function of t minus 1 does is that's multiplying it by 0 when we're less than 1, so it's off. And then beginning at 1, then we're multiplying the function by 1, which doesn't change it. That means that the function is now just itself, not being multiplied by 0 anymore. And the unit step function can also be used to write piecewise functions. So given a piecewise function f of t, which is g for t below a and h for t greater than or equal to a, it is the same thing as this. And to see this, what you want to do is just plug in any point below a and see that it becomes g of t. So if we are below a, then that is 0, because we are less than a, so the unit step function is off, and then we just have g of t. And if we are above a, then that means that this is 1, and this is 1. Now we're looking at this case if we're above a. And then it's g minus g plus h. G minus g goes away, and we have h. So that's why it's then h above a. And that kind of thing will be useful because we will be dealing with piecewise components in differential equations. And we'll learn how to find Laplace transforms involving this unit step function. And this is our second translation theorem. So notice that because the Laplace transform of t is an integral from 0 to infinity, anything to the left of the y-axis may as well be 0. And our second translation theorem will be concerned with the effect of horizontally shifting a function to the right by a, like this. And that shifting to the right, where it's 0 to the left of a, that is f of t minus a times unit step of t minus a. F of t minus a, that's our horizontal shift to the right by a. And then unit step turns it on once we get to a, and it's 0 below a. So our formula for the function shifted to the right by a is this. And this is the second translation theorem. The Laplace transform of a function shifted to the right by a, which is turned on at a, is e to the negative as times the Laplace transform of the original function. That is useful in its own right for finding Laplace transforms involving piecewise defined functions. And also very important is the inverse form, which just says that the inverse transform of this right-hand side is the left-hand side. So when we're looking at an inverse transform of a function, if we have an e to a power of as in it, then that's begging for us to use this, where we just find the inverse transform of the part without an e to the negative as in it, and then shift it in this way with the unit step function. So let's do an example. What is the inverse transform of e to the negative s over s? Well, that's e to the negative 1 times s times 1 over s, and that is of this form. So this guy, f of s is 1 over s, and then f of t, which is the inverse Laplace of that, is just 1. And the left-hand side says that it will be equal to f of t minus 1 times unit step of t minus 1. And if we plug t minus 1 into our f of t, what do we get? If you got 1, then that is correct. And that is because if we plug t minus 1 into the function y equals 1, it's still just the function y equals 1. In other words, it's 1 no matter what input we put in. It's just constantly 1. So therefore, it outputs 1 at t minus 1 as well. It always outputs 1. And 1 times anything is itself. So the inverse Laplace of that is u of t minus 1. Sometimes we need to combine both translation theorems. Let's find the inverse Laplace of this guy. So first, remember that whenever you see an e to the negative as inside something you want to find the inverse Laplace of, that is begging you to use the second translation theorem. Okay, so now this looks like our e to the negative as times f of s, where this guy is our f of s. So the question is, now what is f of t? Let's answer that on another slide. So we're considering f of s is 1 over s plus 1 squared. And we want to find what is little f of t of that, because then we can stick that in this formula for the inverse Laplace of this guy. So what's the inverse transform of this? Well, we have 1 over s plus 1 squared. We know the inverse transform of 1 over s squared. It's t. So this looks like a translated form of 1 over s squared. And it is minus -1 all squared. So where g of s is 1 over s squared, this is g of s minus -1. So that's like our f of s minus a there. Okay, and also we know that the corresponding g of t, the inverse transform of 1 over s squared, is t. So therefore, this is, by that first translation theorem, e to the -1 times t, right there, e to the at, times little f of t. In this case, that's our little g of t, the inverse transform of the unshifted function 1 over s squared. So times t. So that slide was to find the inverse transform of this component. And what we just found is that f of t is t e to the -t. And by our second translation theorem, the inverse transform of e to the -as times big F of s is that, in this case, that's f of t minus 2 times unit step of t minus 2. And we found our f of t there. So this is our f of t minus 2. And then times unit step of t minus 2. So slightly simplifying that exponent, we have our inverse transform of that function. Now let's conclude with an example. We will solve a differential equation using our newfound translational properties. So let's solve this differential equation. So step 1, we take the Laplace transform of both sides. We use linearity. And then we use our derivative property. The Laplace transform of y double prime is s squared f of s minus sy of 0 minus y prime of 0. And the problem tells those to us, there and there. So both of those fortunately go away. And the Laplace transform of y prime, that's our s f of s minus y of 0. And Laplace of y, another word for that is just f of s, is the Laplace of that right-hand side. Okay, now every term here has an f of s, so let's factor it out. We have an s squared minus 4s plus 4, all times f of s is the Laplace transform of t cubed e to the 2t. Okay, now we want to find the Laplace transform of t cubed e to the 2t. And what we want to do is look at our properties. Whenever we have an e to the something inside of a Laplace transform, that is asking us to use this first translational property. So for this, we want to use that. And we can think, okay, well, the Laplace transform of t cubed, we know that that is 3 factorial over s to the power of 3 plus 1 by this property here. So that's 6 over s to the 4. And then multiplying that by e to the 2t. That 2 is our a, so we just shift it to the right by 2. So replace that s with s minus 2, and we have our Laplace transform of the right-hand side. And notice that the left-hand side, s squared minus 4s plus 4, that is the same as s minus 2 all squared. So f of s is fortunately quite nice to solve for here. Dividing both sides by s minus 2 squared, we will have that f of s is 6 over s minus 2 to the power of 6, dividing by that s minus 2 squared. Okay, great. And that's not bad at all to find the inverse Laplace of. So now y is the inverse Laplace of that. And looking at this, we might think, okay, this looks like it's been shifted. This looks like it's possibly the first translation theorem as well. Or how I typically think of it is the following. I regard the whole inside as a single thing. Now it looks like 6 over blah to the 6, which is a number over blah to the n plus 1. So let's make it look like that. This is 6 over s minus 2 to the 6, which is 5 plus 1. And what we want is a 5 factorial up here in order to make this look like this. Now it's of the form n factorial over s to the n plus 1, you can see, except with this shift to the right by a. So what we did there, remember, was we wanted an n factorial up there, so how do we get that? We just stick it there and divide by that same thing. And now 6 over 5 factorial, that's just a constant. 5 factorial is 120. It's linear, so we can pull out constants. And now by the first translation theorem, right there, together with our inverse Laplace, that is e to the power of 2t. That e to the at there is our e to the 2t times the inverse Laplace of the unshifted function, and the unshifted function has an inverse Laplace of t to the 5. And 6 over 120 is the same as 1 over 20. So we have solved our differential equation. And notice that that is much nicer than having to use method of undetermined coefficients for something like this, especially since we would need to multiply our guess by t squared, since 2 is a double root of the auxiliary polynomial. So that does conclude chapter 7.3. Have a great one.